So as usual, the brief recount of the previous episodes. So we are talking about information, and we decided to characterize information by how much uncertainty it decreases. And then we decided to measure this uncertainty by the number of questions which could be hierarchically diminish this uncertainty by dividing it into classes. And so, in particular, if we measure it in bits, we, for equally possible an object, we quantified uncertainty as a logarithm of n. Then, if out of these n objects they enter with different probabilities, we quantify it by the Gibbs entropy, that's a minus here, which is log of pi sum, so it's a mean value of a log. Here it's just a log because the mean value is equal to, and here we quantify it like this. And then in the kind of maximal level, which seems to be the most sophisticated measure of information transfer, which today we'll find a little bit more general, it's a mutual information. It says that if you have something which goes from B to A, and A is what we receive, measure, predict, and B is what is reality, then generally it could be that everything here is precisely what is here, and then what we obtain is entropy of B, of a distribution of B. But it could be that it's actually less, and when it's less, it's characterized by this value, which can be also said that this is S of B minus S of B under condition of A. Okay? And then we discuss that all this is based on the fact that we know the probability distribution. But if we don't know the probability distribution, because generally we measure something and we want to know what is the distribution for this quantity, and what we ended last lecture is that whatever you measure, you generally, and it's a very general framework, you can present your measurements as that you measure quantities, let's say Ri, which is actually sum of P of R, some quantity R, over all possible values, or as an integral of a distribution of X, R as a function of X over dx in a continuous limit, and then the probability which appears would be an exponent of all such things. So if we measure energy, the probability will be exponent of, it will be Gibbs probability distribution or any other quantities. It's a very, very general framework which works from neurons to black holes. And then we also discussed, and that was the end of the last lecture, that any extra measurement put extra constraint on our probability distribution, and then it must lower the entropy of the resulting distribution, at least it is non-increasing. And if this change delta S, which could be say that it is S of our system, let's call it A, and minus the change of our system with a measurement device attached, this is now would be delta S, and what we ended up, and it will be the beginning of this lecture, and its main subject is the price of it. So how much price we pay getting this information, and of course it goes back to this famous demon Maxwell, and it's essentially the following statement, that if you have this delta S, you diminished your entropy, then you increase your free energy. As we discussed, the free energy is something which is the energy you have minus the information that you don't have, which is entropy. So the higher the information, the less energy you can do. In a moment, maybe at the end of this lecture, we will see that maybe this would work the same, for example, in the market. This is your money, this is your information. The less information you have, the less is the purchasing power of your money. And the same is the less is an ability to do work. But on the other hand, if you diminish your entropy, then this is less, then this is more, but it's the first law of thermodynamics, which is energy conservation. So it tells us the following simple truth. If you do all this measurement and they find a temperature T, then you must do work. Any this thing works, it requires that you T S of A minus S of A and M. And it is exactly like Maxwell said. He said, imagine that we have a box and it's divided into two parts. And we know, for example, that the molecule, just one molecule, it makes a chaotic thermal motion. Everything is under temperature T. But we happen to know that this molecule is in the right side. How much we know? Well, we diminished uncertainty twice, which means that our change of entropy is just a logarithm 2. Well, in bits, it's just 1 bit, right? So we have 1 bit of information, choice between left and right. Well, said Maxwell, look, it has a price. We now can do work. We can apply here something, put it like this, and let this molecule to hit this wall. Because there is vacuum here, eventually it would move it all the way, raising this weight up. And so we get work out of it. What is this work? It's exactly this. Okay? And it is exactly the subject that the PhD student discussed with Professor Einstein in the corridor of Berlin University in 1924 and wrote his thesis a couple of years later that actually there is no paradox here. It is just that if you get some information, it gives you ability to do work, which means that to get this information, you must do at least the same amount of work. And everybody seemed to be happy at this point. And then, some 40 years later, people started to worry. Well, we did respect a first law of thermodynamics. But what about the second one? We just turned a thermal energy of this molecule into work. Okay, then let's measure it again, do the measurement, spend this work, exactly the same amount, and then do again work. So it will be no energy gain or energy loss. Imagine everything is perfect, you know, and the person who actually observes it is kind of a person which we call M, after Maxwell or after measurements. So this demon which observes, it's a measuring device, and if it's demonic or ideal, it just does not dissipate. But it's a perpetuum mobile of a second kind, right? We do something which is turning thermal energy into work. Just move it up. And then what people started to worry at late 50s, and the resolution of it came due to Rolf Landauer at 60s, who actually coined the sentence which I put as the title of my course. He said, information is physical. And so what he said that this work that we do, let's we call a work of measurements, M. Okay? And generally, it could be even more generally, because we now attached measuring device, it's now part of our system, that there could be some change of a free energy of a measuring device, whatever it is. But if you wanna do cycles with it, say the Rolf Landauer, you really need to do a full cycle, because look, when it moves this system up over here, there is no left and right anymore, right? You need somehow to put your wall back. And this beautiful experiments which were published in Nature a few years ago, they were actually really doing this. But then you kind of compress your phase space from this to this. Or in other ways, you need to erase information. Because what you gain after a cycle, you change the state of a measuring device. If you will be doing over and over again, you will be adding bits and bits and bits of memory to your measuring device. So what Landauer is saying, you need to erase. If you want a cycle, return everything to its previous situation, in which you would have no change of a free energy of a measuring device, and you erased the information or change of entropy that you've got. Okay? Now, your, let's say this was delta S1, your delta S2 would be something which would be S of M, and you would also change delta F would be T delta S2 Sm minus delta Fn. So you need to erase this times temperature, that would be of energy, and you need to return your device back. So this would be work of erasure. Now, if you add it together, so you add Vm plus Ve, what you would get? You would get T, and this will come with a minus, right? Both come with a minus because now you are erasing information, so you're increasing the energy. So you would get Sa plus Sm minus Sam, and this guy cancels that guy. So this is the cycle. And what we find here is mutual information between measuring device and your system. It's absolutely independent of whatever changes you do or whatever entropies you do. The energetic price, and this is, as we discussed, as any, so this is mutual information between A and M, and it's non-negative, okay? And in particularly now, it's slowly turning from physicists, paradoxes and all this into pretty interesting subject which is about to be practical, namely computations. Because when you do computations, you do irreversible steps. In principle, you can build a computer which is totally reversible. But generally, you do AND operation, or OR operation, or XOR operation, and they are irreversible. They compress space. Well, for two possibilities, they will give you eventually R. And what Landauer tells you, that they must be that every time that you do it with a bit, T log 2 of 2, which is T, that's how much heat you need to expend. And of course, present devices are still a couple of, maybe 2-3 orders of magnitude above it because they work at a finite rate. But what people already did and measured it, that as you decrease the rate with which you do this computation, the heat that you release goes to this limit, okay, and for every per bit. So this is the picture which tells you more or less the energetic price of all this. And again, as we discussed, you see how it shifted focus from Carnot, who was obsessed with efficiency of thermal engine, to Shannon, who was interested in communication. To the present day, we are mostly interested in computations. And then we ask, what is actually size of computation? Question?
It's a comment. I think that you can get down to the Landauer bound only under the condition you have an infinite amount of time.
Absolutely. Right. That's absolutely right. All this is always inequality, and all this inequality always means adiabatically slow. And that's why all present-day devices are still 2-3 orders of magnitude, but they're getting better, and not only by making it slower, they actually want to make it faster, by just eliminating dissipation of the elements and irreversibility. But there is basic irreversibility just in erasing information. This is essentially about it. So now, this was the first part. Now I want to return to, not even biology, to psychology maybe, and ask the following thing. We use information, transfer, etc. But has it any relation to the way our brain works? Because information for us, initially, originally, is the way that our brain receives something and then acts upon it. And about the same time as Brillouin at late 40s explained to people what actually Leo Szilard did introducing this bit of information, at early 50s, people did fantastic experiments. There were people who were psychologists. And those experiments, as surprisingly for psychologists, standed the test of time. They are reproducible. And they did a very simple thing. You have a phone book. You need to find a name over there, right? How the time which it takes grows with the size of the phone book. There are a small city, there are a big city. What would be your guess? Like this. Logarithm. Okay? Good guess. And then American psychologist Hyman did a much simpler experiment. He said in advance that you will be given numbers out of 1 to 20, and then out of 1 to 30, or you will be given a letter of alphabet, you just need to name it. So on the screen appears a letter, and the person needs to name it, and then they measured an average response rate. So again, if there appears a number out of 20, the time was growing with the number logarithm 20, logarithm 40, logarithm 60. Then they were educated people, they started to give different probabilities to different numbers, or use alphabet, because for alphabet we already have a built-in probabilities, because those of us who read anyway. Okay, so what would you expect? How your information, how your response time would behave in this case? Be larger or smaller when we ascribe, when we have with not equal probabilities?
Smaller.
Smaller. Why?
Because entropy is smaller.
Exactly. Because the degree of uncertainty is smaller and unbelievable. Just look at this data. It's Hyman 53. How beautifully all these things lay down on it. Then they went one step further. They made next number correlated with the previous one a little bit, which means that apart from pi, they divided also pij, namely the conditional probability of observing j after y. Again, the response time went down exactly like an entropy of English that we discussed, and it was more, there was constant of proportionality is the same. It was important that it was a learning curve. So when a person comes, he doesn't know this probability. Our brain learns it on the fly. So it takes a while, and then it gets into a constant response time stop changing, and this time is proportional to it. And then Higgs did even better experiment, even though it was not that. Higgs was actually 52. But in Hyman experience, all come together. He prescribed response time. He said, you give an answer in 5 seconds. Okay, good. Then, because you give an answer in 5 seconds, then some answers were evidently wrong. Right? So there was this probability pi ij, but not now with the subsequent numbers. This was a signal, and this was an answer or response. And they weren't necessarily the same. It was not delta ij. It turned into delta ij in the limit of very large response time. So he was measuring this set of probabilities, of which, of course, you can obtain marginal probabilities pi, which is the sum over j of pij. The same you can get marginal pj, the sum of, we know that this is eigenvector of this matrix anyway. Then you can get an conditional probability. What is the probability of giving this response if you given this stimulus, which is apparently pij divided over p of I by a chain rule? And then you can compute mutual information by this formula, where it is, this one. And believe it or not, this mutual information was proportional to the response time that was set at the beginning. So when you increase the response time, the mutual information increases. Of course, they're getting more and more correlated. I mean, the stimulus and your response. And that was a very powerful demonstration. Yes?
Do they have to present the stimulus with the same distribution as the underlying letters? Like if they're showing letters, does it have to
In
follow?
this case,
Yeah.
they were given stimuli equal probable.
Okay, so P of I is
P of I is not about statistic of
Right,
stimuli.
okay.
It's a statistic of you making a mistake, right? So it's not about the probability distribution of what stimuli you get. They will take it equally. But this is the signal, and this is your answer. And it's not delta ij because you're making mistake. It's time to short. So even when you turn tables and set the response time, then you increase response time and you see linear growth of mutual information, and it's a non-trivial task. You need to compute it. It takes a pretty large statistics. So this is really was a very powerful demonstration that this is a very useful technique, and apparently maybe one of the first examples that mutual information is essentially the right quantity to characterize error-making channel or noisy channel as Shannon. It all goes back, I mean, to Shannon eventually and to Szilard. But this is important. Now, this is purely speculative. This is just a papers which appears last maybe 3 or 4 years, 17, well, maybe early paper 2009, is the most interesting thing, which probably is the main scientific problem of 21st century, which is scientific, not practical, which I think is consciousness. Can you measure consciousness? Really? What it is, right? There are skeptical people, and in a sense I am on the side, because the same question people asked 60 years ago was asking, what is life? What is life? What is this difference between something which is alive and is not alive? I remember when I was a kid, there was this big philosophical discussion, and somehow 40 years passed, and it's much less exciting. Because I say, okay, life is something which does this. And as we discussed in the first lecture, life is something which interrupts a flow of energy from low entropy source like sun to high entropy sink like our air. So in a sense, it's a definition which is operational. Life is what does this. And then you ask how much you can measure. In particular, you can measure it by processing information. Can we do the same with conscience? And people are now trying to do it. Maybe it would all fail, I don't know. But it's a brave attempt, I think. They say that you have a question?
Yes. You said the mutual information increased linearly with the timeline?
Yes.
Is there an explanation for why linearly?
Because it's usually the response time is proportional to the degree of uncertainty, which is how much information you get when you really get it. So essentially, it's like it was proportional linearly to the logarithm of n. It's all the hierarchy kind of the same thing. Your brain reacts faster when the uncertainty is smaller. You can make mistakes with it, that's okay. But then again, when uncertainty is larger, it takes it more time to get, or you can put it other way. When you increase time, you do it better. So the correlation between signal and your response increases. That increases mutual information.
Okay.
But linearly.
I would have thought it would take.
Yeah, it's logarithmically with respect to number of elements, but it's linearly with respect to entropy this or entropy this. Because entropy is a rate, it's a mean logarithm. Of course it's logarithmically. By the way, if a menu in the restaurant is not alphabetically ordered or divided into desserts, main courses, etc., the time grows linearly. Of course. It's only because we work by subdividing, right? That's how we get logarithm, right? We subdivide. There is, if no subdivisions, then it's linearly. Well, there are very, exotic cases. Anyway, returning back to consciousness. So what the idea is the following. We can now measure very well the brain activity. So really, we can measure a lot of neurons firing simultaneously in many cases. And then we ask what to do with all this data. And I think it's a very beginning. There was, of course, all these beautiful old works by Galich where they just measured correlation between different neurons, treated it as an Isaac model and get a very beautiful statistics. But now people do more. They say, let's say that we have different brain regions and they have their own statistics. So for every region, we can compute its probability distribution. Good, then we can compute its entropy. Then for another region, we can get probability distribution and get its entropy. Then for this region, we can get.
Can you just clarify, what do you mean by the probability distribution of entropy?
You have essentially, let's say, 5 neuron region, okay? Every neuron is a spin. It's either fires or not, okay? At every moment, you have 3, 4, or 5 spins firing, okay? So you have this 5-dimensional probability of, which started from none of this fired and all of them fired. Okay, and then you have a table, 5 rank tensor, which will give you this probability. You can also but essentially it's neuron is good because it's yes, no, fire, not fire. Okay, it's bit. Neuron is a bit. It's really very powerful technically thing. So you can get the probability distribution of different regions, and then you may also compute the probability distribution, which is very complicated. What is really technically nobody knows well how to compute probability distribution of a multidimensional distribution because it's exponentially difficult. You need to get statistics which fill all the bins. Now there are codes like limitl, which tries to compute this probability just by getting the stream of data. Like you try to encode this data, you encode it beta and beta and beta, and at some point you stop and say, okay, this is my rate of encoding, it is the entropy, at least for now. But what these people now try to interpret as constant is the following, is a mutual information between different regions of brain. They say if this mutual information is small, we tend to interpret it as a non-conscious activity. And we all know that it's a lot of non-conscious activity. We drive from home to work and we don't remember a thing about it. This is a very, highly organized activity, getting into a car, driving, stopping on a traffic light, usually leaves nothing, which means that we usually not very conscious. There are many other things. We breathe, so our brain works most of its time, but at some activities, you see that the mutual information is substantial. And the idea is
Are you suggesting there's a phase transition?
No,
With this consciousness?
not
Or is it a
necessarily.
continuous process?
Not this. What I am saying is, which I like, by the way, most, is that there's no transition here, and there is not much qualitative difference between conscious and unconscious, or you and me, or me and a little animal, etc. It's a quantitative difference, right? So it's like life. What is life? I mean, yeah, okay, it's something which interrupts or self-organizes, self-reproduces. Now,
No, but when you say self-organizes, now you're beginning to talk about phase transitions.
I don't think it's phase transition. It could be. Nobody yet discovered it. It's called integrated information theory. It's a very recent subject, and the idea is that you compute mutual information between different brain regions or brain activities, and it's always non-zero. But it could be small, or there may be a threshold, something which passes through it. Because, for example, when you drive, you may remember one traffic light on this way, which means that it was like, not totally unconscious, but also neither totally conscious. And there are many things here. The way we speak, for example, when we usually fire 4 words per time. We make pauses after 4 or 5 words. It's also probably a complicated process. But what I like about this idea is that it tries to quantify it. And the mechanism, the instrument is the same. It is this thing. Probably there will be phase transition in some sense, but nobody yet observed it here. There are people just trying to start to quantify kind of, activity which cannot be divided into parts. Something which really involves a coherent response.
Right. It's as if things synchronize.
It's not only synchronized, it's correlated. Correlation is a weaker notion than synchrony, right? It could be that those correlations are kind of delayed in time. But just when you compute the entropy here and the entropy here, together the entropy is less. So somehow it's kind of, the probability distribution is less spread when they are together. I don't know, that could be. Okay, now I want to follow this example and pass now from a very general brain response to a very particular brain response, which was, by the way, the first example of really doing data, biological data and using information theory, and that's Laughlin 81, it's already later. Response, just response. I mean, you look at me, I look at you, our eye sends a signal, right? Well, there is an eye, it is just a sensory neuron which goes not even to brain, to the first station on the way to brain, and you put here light, and you just measure, okay? And so what you measure? What Laughlin found that he just measured electric pulses, namely how many pulses run through this sensory neuron. It reacts on contrast, not on light intensity, but in light contrast, okay? So you measure response, which is a number of pulses, as a function of a contrast signal, right? What would you choose? Imagine that you God Almighty, and you are creating, this is day 4, all right? So you're creating animals and all this. So you need to create a response function, right? Well, it must be monotonical, namely, if there is more signal, there will be more response. Let's say you want to divide it into weak, medium, and strong, like just 3 levels, right? And here you have, so you can take it linearly. So weak would be this, medium would be that, and strong would be that. And that's your dynamical diapason, you just don't get more response, right? Your neuron cannot fire more. Or you can take it and use a convex function, right? You can say, yeah, I don't much care about strong signals, but I really want to take something like this. So now my weak would end here, my medium would end here, but most of strong signal would be kind of, right? So you really change your response to weak signals. I don't much care about strong signals. By the way, you know what works like this in our sensory organs? Ever heard word decibel? Our ear senses logarithm of a signal. So we aren't, afraid when we hear a lion somewhere, but we do hear a whisper of a brook somewhere there. It's a logarithm, that's why we measure it in decibels, not actually in analytic. But this is not what God Almighty made, and that is not what Laughlin found for a fly. He took a fly and just measured this. He found something very different. He found this function.
Yeah.
Okay? And then this guy did this very strange thing. He took a camera and went to the lakeside in a swamp where this fly lives. This is a fly which lives in the nature. And what did he measure? Camera, video camera. He measured the probability distribution of signals contrast. A fly lies like this. So he just took camera, moved it horizontally with a constant speed, and measured the statistics of a contrast. And it gets some probability distribution, P of C, of the same C, which look like this, of course. And any probability distribution has a maxima. What is the relation between these two blue curves? One is integral of another, apparently. Can we interpret it now, as we are educated people with no information? So now, if I look at this, right? So now here, this is my weak signal, you see? And it would come here. This is my medium signal. That somehow I did not make it exactly right, because the maximum, of course, must be where this, so here is the maximum, right? That's where my inflection point. So this is the probability distribution like this. So you see that this is my weak, this is my medium and strong. And what we can say about this, so all these signals would, with these amplitudes, would give me a weak response, but their probability, the area under the curve is the same as area here and the same as area here. This is actually the statement that this curve, its derivative is this one, right? So what essentially God Almighty and Fly does, it makes a response function exactly dependent on the probability distribution. That's how evolution works, right? Evolution is a way to encode information about environment in the genome of its inhabitants. So that's what Fly has. And as a result, on this, if you say that this blue is a G curve, right? So you have Y with a G of X, and if this is P of X, then P of Y is constant, right? It has three bins, and they all have the same probability. But this has a maximal entropy. If you ask what is the, you have a distribution in the finite interval, the only thing that you require is a normalizability. What is the maximal entropy? Which distribution corresponds to maximal entropy if no other condition is given? The answer is constant distribution. That's what precisely this Fly does, and many other things. And this was a very powerful demonstration to what extent information theory really determines it, and to what extent it is this simple idea that the entropy is the rate of information transfer, and what the Fly does, it maximizes the rate of information transfer. Okay? Questions? Because now I finished the second part of the lecture, and I'm switching to the third part, which will be mine. So, what about life? Are there questions about life, conscience? Yes.
I feel that defining life as interruption of a flow of entropy from low entropy source to high entropy source is a little tenuous.
I was joking. Of course, it's just a part of it. Of course, life is, first of all, must be something which self-reproduces. And this is a much more subtle informational content to it. So, sure.
My other example was a refrigerator.
Yeah, well, look, many things interrupt the flow. Because you cannot do it other ways, so you just do it this way. Okay, so now, if there are no other questions, I want to make a little generalization of mutual information, which turns it into more powerful. Let's call back-Landauer divergence, or sometimes it's called relative entropy, and it's the following thing. You remember we were talking about hypotheses. So you make a hypothesis, then you get the data, and by Bayes' formula, you try to estimate what is the probability of this hypothesis under this data. Okay? Now imagine that again you're in the same situation, you have I from 1 to n, and your hypothesis is Qi's. So you guess the probability. You say, I believe that the probability of an event I, or level signal I, is Qi. How many experiments you need to support or to reject this hypothesis? Okay? Imagine that the true distribution is Pi, not your Qi. Okay? Then you do many measurements, and then something event I, how many times it happens? It happens, as we discussed many times, Pi times n. I'm using Stirling formula over and over again because there is something, like when I tell you 3 times is true, it's some kind of reinforcing. So every would happen with this, but how would you guess what is its probability based on your hypothesis, right? So I'm asking, what is the probability of this evidence under your hypothesis? And this is Q, and this is, right? You would say that the probability of this happening is the probability of this that many times, namely in this power, right? Times the number of possible permutations which you could have. So this would be sum over I, and this will be product over I, pin factorial. So this is your probability of hypothesis under your measurements or your experimental data, right? Good, okay, so then you can say that this is everything which is E. Again, I'm not doing computation because it's a Stirling formula, and we already, it will be minus n sum over E logarithm of pi logarithm pi over qi. Okay, so if you write this as an exponent pin logarithm qi, just raise this over there. Then when you take in exponent of this, it will be exponent of logarithm of this. You use Stirling formula, you get this. This is probably most important quantity, I mean, from black holes to... So again, it is called Kullback-Leibler divergences. It's usually defined like this. So let's write it again. It's pi log pi over qi. It is something which is effectively measures how different is your guess from reality. It's not a distance between two distributions. It's not symmetric with respect to P and Q. There is no symmetry between reality and our hypothesis. This is an important message. It turns into zero, it's not negative, absolutely, and it turns into zero only when Pi is equal to all Qis. Whatever any Pi is not equal to Qi. It has many properties of distance, but it's not distance. First of all, it's not symmetric, triangle quantity, etc. And it's a relative entropy. And of course, mutual information is a particular case of relative entropy, right? When our distribution, Qi, is a product, right? So when we have a probability of every event, right? So, for example, if I remind you that I of A and B is a sum of probability of AI, Bj over all I and j as the logarithm of P of I and P of Bj divided by, divided by P of I and P of Bj, that's a mutual information. Put here any hypothesis which is different from this will be relative entropy. Okay? So relative entropy is a slight generalization of it. And the last thing that I want to know is how to make money out of it, because this is a famous work of Kelly. This is now 55 probably, but recently Losha Kitaev made a very beautiful generalization to this work. How to make money. So imagine you are doing bets, simple bets. So for example, there is a coin, so you wouldn't go and make money out of a coin. You're smart. You actually know that this coin is uneven. You have an information that it has probability P, which is larger than 1/2 to be on one side. And so 1 minus P less than 1/2 on the other side. And now you want to make money out of it. The question how? What would be your strategy? You just graduated, you're a poor student, but with a lot of knowledge. You want to get rich immediately or a constant stream of income. Always. So you want to maximize your return, right? What is the maximal return that you get? Let's say that every time you guess right, you double your money. Every time you get wrong, you lose your money. Okay? This is a simple question. Then later we consider generalization. But let's say for now, you bet right, you doubled your money. So what is the mean maximal rate of returns that you can get after n such things? You double your money in the power n, but it happens with the probability in the power n, right? P is larger than 1/2, this is larger than unity. It exponentially growing with n. It's arithmetic mean, and it's maximal, which means that the fraction of money that you put on this is equal to unity. So you put all your money of it, you go on n time. What's wrong with this strategy, market strategy? Yes?
The probability.
It's probability going to zero. So even though the mean return growing, the probability of mean return is p over n, and it's very fast going to zero, right? So you don't want this. So what you really want to do, you want to be smart. You want to really take into account that p is not unity. If p is unity, that's what you do, right? But p is not unity, so you need somehow to make it fractional, right? So you want to put f on p, and put 1 minus f on 1 minus p. Okay? There's sometimes people, when I teach a regular course about this, the students say, why would you put on 1 minus p? It's a kind of a improbable part. You just keep some money yourself, but that's not enough. You can have just less money, make less money working. You really want all your money work. So you really do fraction, because if you don't use some money, just forget about it and use the remaining part. So now, let's see what kind of, so now what you have, your return would be 2 times f, because you put this fraction, right, in some power n, out of this n, and then you would have 2 1 minus f in the power n minus n. Okay? So that's essentially, after n events, there will be such n where you get on this side and n minus n when you get on this side. So now let's do what we actually do when we compute Lyapunov exponents and all such things, which is always the right thing as we learn. Always look at the logarithm. Always look at the exponential rate. So let's write it as an exponent of n times some lambda, and this lambda will be function of f, and apparently this lambda as a function of f is 1, which comes out of this 2 in the power n, right, plus p log, logarithm, if we took exponent, like let me take 2. Everything is in bits, right? So it will be log 2f plus 1 minus p log 2 1 minus f. Okay? Now what you need to do, of course, is to look for extremum. So you're looking for a maximum of geometrical mean, not arithmetical mean, right? d lambda over df equal to 0. So if you differentiate this guy, you get p over f, you get p over f, so it of course f equal to p. It's called proportional gambling, and now when you look at it, your lambda maximum now, it's, let me write it somewhat idiotically, log 2 of 2, which is this unity, plus p log p plus 1 minus p log 1 minus p. What is this? Is this a minus entropy of our distribution? And what is that? This is the entropy of a uniform distribution. If we would have both sides of a coin the same, we would have one bit, right? So essentially, it's, as they call it, S of u minus S of p, right? And one must be less than another, okay? Now, it's pretty easy to generalize it for a situation where you have different pi's. Of course, you would have fi's, how much you put on every I. But you can also have different rewards now, gi's, let's call it gi. So this situation was p1 is equal to p, g1 is equal to 2, g2 is equal to 0. But generally it's, and now it's pretty straightforward to show that lambda is, where is my lambda? Yeah, it's a, logarithm of pi, no, not logarithm, pi. It's pi logarithm of pi over gy sum over I. Okay, so before this was 2, and came over there, and this was an entropy P of I. Now, you may say, okay, but somebody sets the rewards, right? For example, you are betting on a horse track, there is an operator of an hippodrome, right? And he sets these rewards not arbitrarily. He generally sets for somebody's probability of winning smaller, he sets high reward, and less. So it can set the rewards gi, which is just 1 over pi. And that's the end of your winning strategy, because this is always 0 over here, right? But it's even worse, because generally they do it like this. Because there is some operational cost, of feeding horses and all this other stuff. So you would be, of course, losing money, which of course most people do. So what is the hope in this situation? The hope is if the operator using wrong probability distribution. So he uses QIs, but you are using PIs. Okay? And what will be then the result of all this? This would be your lambda, which is minus log z. You always need to pay operational costs. You always need to feed the horses, etc. And plus g of p and q. In a more general setting, when you're using some q prime and operator using q, what will be standing here is minus log of z plus d of p through distribution and q minus d of p and q prime. And that's your growth rate. Okay? So you see that it's this relative entropy tells you something which may look unexpected. What is this q that operator gets? By the way, if you open economic textbook, they have this beautiful and totally abstract theory of market equilibrium. And it tells you that the market is at any moment is in equilibrium and all prices really reflect the relation between demand and then it always corresponds to true probability. But essentially it's not like this. So what operator has, it has tables of all the previous events. And this is is how compactly it can encode it. The better you encode it, the more compact it, the closer you to the real entropy of a signal. Your distribution is different from a true distribution. But the closer you come to it, the better. So, in a sense, Kelly formula tells the following thing. Somebody who can encode the same tables of data in a more short way gets more money, exponentially proportional to the rate of this difference. Okay? And of course, this is one of the only few applications of it. But now let's reiterate at this point and then turn to questions. So, what was the subject of today's lecture is first the energetic price of information. And we found out that in a simple case it is just entropy or entropy change. But in a more complicated case where we want to make the whole cycle, namely recording information and then erasing it, it would be mutual information. So you cannot, for free, record and erase. You need to release heat. Again, this is something which despite a sheer triviality, this is, arithmetical operations that they did this, you can make it more trivial. Conceptually, it's far from trivial. And it took a lot of arguments before people really started to call it Landauer formula. So it tells us that if you make a cycle of getting information and erasing information, you pay the price. T times mutual information. And this is mutual information appears in a totally new context. Okay? And then what we have seen is that a little generalization of it, which tells you that the rate with which you disprove your hypothesis, it essentially tells you that the probability of your hypothesis being true exponentially fast turns into zero. The rate with which it goes into zero is a relative of Kullback-Leibler divergence. Okay? And on the other hand, if your guess, your hypothesis, is better than somebody against whom you are betting, then you get money with a rate which is again the relative entropy between your distribution and his guess about it. Okay? So that's more or less the statement. I had as I started, I was still undecided whether my last lecture will be quantum information or stochastic walks, Google page rank, and all such things. But it seems that there are less people interested in quantum information, and it's very difficult to get quantum, these things in one lecture. So the last lecture will be some more example of life, money, etc. I'll also show you that this strategy of proportional gambling, it's actually, where is this? Yeah, this one. It's actually used by bacteria in what is called phenotype switching, and then we consider random walks, a new modern form of second law, and Google page rank algorithm. That will be next lecture. Okay, thanks for